Hi there. My name is Zach Rothman. I am working on the design and evaluation of a low-cost in-situ 3D vibration sensing array for an LPBF recoder arm. That's a lot of words, but essentially, all I'm looking for is unhealthy metrics within an industrial 3D printing application. So LPBF stands for laser powder bed fusion, which is a method of 3D printing or additive manufacturing, where a layer of metal powder is laid down across the build area by a recoder system. Part of that is the recoder arm and the motion system to lay out that thin layer. It's very important that that layer is smooth so that the thickness of the layer is consistent across the build area so that when it is shot by the laser to fuse it together, no one spot takes more energy to fuse than another. So it's pretty essential to have a stable recoder arm. Uh, so my research over the summer was to design and evaluate how useful a low cost in situ sensing array for the stability of that recoder arm and like seeing how viable it was as an answer to a need in industry. So what I did is I took four low cost off the shelf accelerometers and attached them to a $4 Raspberry Pi microcontroller just to see what kind of errors I could detect using this kind of off the shelf, these kinds of off the shelf components. Um, so what you can see on my results page that after a regular jog, I could find that the whoop, I could find that the peaks and valleys of all three accelerometers that I'm graphing are pretty well tied together, and that there's no special separation or spiking occurring, which is nice. We can also see that the peak value for the x acceleration is much, much larger than the peak values for the y and the z, which makes sense because the recoder arm is only moving or only should be moving in the x direction. Uh, for a metric, just to see if I could detect it, I loosened all of the bolts, which you can see up here, the attachment bolts. I loosened them quite a bit to see what I could make happen, see what I could sense. And when I jogged it, you can see that the X values stopped trending together. So you can see here they're tightly trending together. But in this one, they have separated so that the close accelerometer, close to the door, is reading almost double that of the far accelerometer. This is something that we would expect to see if it were wagging back and forth like a dog's tail. The tip of the recoder arm is moving much, much more than the base of the recoder arm. That said, we can also see some pretty high spikes in the Y and in the Z, which is abnormal and would be cause for concern. Also, we can see that when I tapped the recoder arm with a hammer, we could see large spikes in the acceleration. In the beginning of this graph, you can see I have a normal jog for comparison, and then two light hammer blows at the end. So some out of motion axis acceleration is seen on these, which is the Y and the Z. The recoder should not be moving in those directions, so we shouldn't see acceleration in those directions. So we do, which is an issue. Um, so all in all, it was pretty successful. We could see that there are some clear metrics for determining that something is going wrong and that it is pretty cheap to obtain those metrics and obtain that data. Future work would future work would include optimizing the filter performance. I think I Used kind of a gut feeling on a lot of the parameters for the filters, and it would be better to find edge cases and make sure that the filter could detect those kinds of edge cases. Establishing a comprehensive health metric, so things like wear and maybe area under the curve of these kinds of acceleration spikes. We could also develop an algorithm to locate the position of collisions along the length of the recoder arm. So using that same separation of acceleration to possibly determine where along the recoder arm a collision has occurred. Thank you very much, and goodbye.